ever wondered how a machine actually learns to think? I mean, really think strategically? Well, today, that's exactly what we're going to unpack. We'll follow the journey of an AI's mind all the way from figuring out a simple maze to, well, to masterstrokes in a game like chess, outplaying the best of us.
I mean, how can a computer beat a grandmaster at chess? It's a question that feels huge, right? Almost like magic. But what if I told you the answer, the secret to that incredible feat begins with solving a much, much simpler problem?
Yep, you heard that right. A maze. Before an AI can even think about checkmating a human, it has to get the absolute basics down. And that basic is just, how do I get from point A to point B? This is what's known as a search problem. And trust me, it is the bedrock of everything in AI strategy. We're talking about the tech in your car's GPS all the way up to that world champion chess AI.
Okay, so how does an AI actually tackle a maze? Well, you could try the brute force way, right? Just check every single path. But that's a total non-starter. It would take forever. So to be effective at all, the AI needs a clever shortcut, a much more efficient way to search. And that's what we call an informed search.
And the AI's secret weapon here? It's something called a heuristic. Now that sounds fancy, but really just think of it as a smart guess. It's like having a compass that doesn't point perfectly north, but gives you a pretty good idea of the general direction. It's a rule of thumb that helps the AI zero in on the most promising paths and find that goal way, way faster.
So a really common heuristic is called the Manhattan distance. It's super simple. The AI just counts the squares, how many steps up or down, and how many left or right to get to the goal. It's like you're walking in Manhattan and can only move along the grid. Now here's the key. It completely ignores any walls that might be in the way. So it's not a perfect measurement, but it's a fantastic, quick and dirty estimate to point the AI in the right direction. All right, this brings us to a really powerful tool called the A-star search algorithm. What makes it so great is that it combines the best of both worlds. It looks at G of n, that's the actual distance it's already traveled, the known cost. And it adds that to H of n, which is its heuristic, its best guess for the rest of the way. By putting those two things together, it can make a much smarter, more optimal choice about which path to check out next.
Okay, so our AI is a maze-solving champion. Great, but what happens when the maze starts to fight back? You know, what if it's not just a static puzzle anymore, but a game? A game with an opponent who is actively trying to stop you, to make you lose. This is where things get really, really cool.
And that's the huge difference between what we call a cooperative search and an adversarial one. Think about it. In a maze, the walls aren't trying to trick you. They're passive. But in a game, even a simple one like tic-tac-toe, you've got someone on the other side actively trying to mess up your plans. The AI can't just find a path anymore. Its whole strategy has to change. So to deal with an opponent, the AI needs a whole new playbook. And this is where the Minimax algorithm comes in. It's this brilliant strategy that's tailor-made for competitive games, helping the AI figure out the absolute best possible move it can make. The logic behind Minimax is basically a digital tug-of-war. On one side, you have our AI, the max player, and its only goal is to make moves that maximize its score. But on the other side is the opponent, the min player, and the AI assumes that this opponent is playing perfectly to minimize the AI's score. It's this constant push and pull. So how does it do this? Well, the AI essentially becomes a fortune teller. It builds what's called a game tree, which is just a giant map of all the possible futures. Every move it can make, every counter move the opponent could make, it's all laid out in these branches. It lets the AI peek ahead and see exactly where each choice will lead. And the core idea here is that the AI is a bit of a pessimist, but in a really smart way. It looks at every move it could make and asks, okay, what's the absolute best thing my opponent can do to wreck this plan? It assumes the worst-case response, and then it picks the move that still gives it the best outcome. It's planning for a perfect opponent. But there's a huge problem. In a really complex game like chess, that game tree isn't just big, it's astronomically huge. You can't possibly explore every single branch. It's just not possible. So the AI needs one last trick up its sleeve, something to make it think way, way faster. I mean, just take tic-tac-toe. Seems simple, right? But there are over 250,000 possible ways a game can play out. Now, a computer can chew through that no problem. But what happens when the game gets just a little more complicated? Well, in chess, the number of possibilities just explodes. It's not addition, it's multiplication on a massive scale. After just 4 moves each, the number of possible games it's just insane.
more than any computer could ever hope to calculate. So that idea of checking every branch, yeah, completely off the table. Impossible.
And this is where the real magic happens. It's a technique called alpha-beta pruning. And honestly, this is the game changer that made modern chess AIs possible. It's a ridiculously smart optimization that lets the AI just chop off huge branches of that game tree without even looking at them because it already knows their bad paths. So how does it work? It's actually genius in its simplicity. If the AI starts going down one path and quickly sees, hey, wait a minute, this is guaranteed to be worse than another option I've already found, it just stops. It completely ignores that entire branch. Why waste the time? This pruning saves an unbelievable amount of processing power and lets it think much deeper, much faster.
So let's just recap this incredible journey. The AI starts with a simple goal: find the best path. Then it learns to search smarter using heuristics, those educated guesses. After that, it adapts to an opponent with the Minimax algorithm. And finally, to handle insane complexity, it learns to think faster with alpha-beta pruning. It's an amazing evolution. And all of this whole journey from a simple maze to outthinking a grandmaster, it leaves us with a really big question, doesn't it? If an AI can master these games with their clear rules and objectives, what happens when we apply that same strategic thinking to the messy, complicated, unpredictable problems of the real world? Now that is something to think about.